After thousands of years of collective exploration of a whole variety of phenomena that were apparently very different, people realized that they were actually all electric and magnetic phenomena, and that indeed electricity and magnetism were very strongly connected as well. They realized it was all based on charge, that charges made electric fields, and electric fields applied forces to charges. They realized that moving charges made magnetic fields, and magnetic fields applied forces to moving charges. And Faraday found also that changing magnetic fields would make an electric field. And then James Clerk Maxwell got all the data that everyone else had collected and all the laws they'd discovered and tried to make one integrated theory for electromagnetism. So we should adjust our summary here. We know that electric fields are made by charges and changing B fields. Remember, Faraday discovered this experimentally, but we motivated it by thinking about what would happen if we had a moving coil and a stable magnet, or a moving magnet and a stable coil. And we thought they should do the same thing. And so we discovered there was actually a problem with electromagnetism the way it was. And in exactly the same way, Maxwell looked at the equations for electricity and magnetism and put them in as detailed a form as he possibly could, and he noticed there was an actual problem with them. They were definitely wrong. And in fixing that problem, what he did was he added the fact that magnetic fields could also be made by changing electric fields. And this had the effect of restoring the symmetry to electromagnetism, and it made the theory actually self-consistent. It had an extra effect, and that was, he looked at those equations and he saw, well, if I have a changing electric field, I'm going to make a B field. And if I have a changing B field, I'm going to make an electric field. Hey, wait a minute. These can propagate. And so we could have an electric field making a magnetic field, and then a magnetic field making an electric field. And he discovered there was actually a wave solution. So the fields themselves would make one another in an unending wave that would just head off into the distance. And he carefully worked out the speed of that wave, and he discovered that the speed of that wave was the speed of light. Now, of course, that wasn't a coincidence, and Maxwell was smart enough to realize that. He'd figured out the speed of these electromagnetic waves based only on properties that people had discovered in the lab about electricity and magnetism. So the permittivity and Coulomb's constant together would be enough to give you the speed of the wave. And he found out that it came out to be the speed of light, which he had not thought about at all up to that point. And so suddenly he realized, oh my goodness, I know what light is. And in fact, there's the story that that's how he proposed to his girlfriend, Catherine. He took her out and showed her the night sky and the starlight coming down on them and said, Catherine, I'm the only person in the entire world who knows what that starlight really is. Will you marry me? Now, of course, that could have gone two ways, but fortunately history shows that in this case it was successful and she married him. His revised theory of electromagnetism was also unbelievably successful. It explained the existence and nature of visible light, infrared radiation, X-rays, and more, showing how they were all the same thing. It drove the discovery of special relativity, and the theory lasted all the way through to the discovery of quantum mechanics, and even since then it's still a great description of electromagnetism for nearly all practical purposes. So unlike most other waves we might be aware of, electromagnetic waves travel in the vacuum. They don't need any medium to travel in. It's just an electric field making a magnetic field and vice versa. They can be of any frequency or wavelength they like. Remember that the speed is related to the frequency and the wavelength in a very simple way. And so the speed of all electromagnetic waves is the speed of light, but they can have any frequency, and then once you know the frequency, you get a wavelength, or vice versa. The light that we're most familiar with, visible light, starts at a wavelength of around about 700 nanometers for red light, and goes down to something like 400 nanometers for violet light. But in fact, that's a very small part of the spectrum that is interesting to us and that we deal with every day, in fact. Because in the region from that 700 nanometers all the way down to something like a millimeter, that whole region is called the infrared. And it's called that for the not imaginative name that the frequencies are below the red frequencies. And the reason that's so important to us is that that's what we're all emitting. At the kind of temperatures you find on Earth, around about 300 Kelvin, that's the main kind of radiation that everything emits. And so you're emitting that, I'm emitting that. That's why some animals can see further into the infrared, because that's a very handy thing if you want to figure out where all the animals are. We see in this visible range because that's the main frequencies that the sun's emitting, and so we can see reflected light from the sunlight most easily in that range. Above the violet, there's another band called well, I guess this isn't very imaginative either, we call it the ultraviolet. And this goes up to wavelengths of something like a nanometer. And though the sun peaks largely in the visible light, there's still a fair bit of infrared radiation coming off it, and indeed quite a lot of ultraviolet. And this is a little bit tough on our skin, and so we have to hide from that. Well above that, we have a large band that's called the X-rays. And this might go up to something like a wavelength of a picometer. So very high frequencies indeed, if you work out what those frequencies have to be. They're originally called X-rays because when they were discovered, no one knew what they were. But it wasn't that long before people realized that this was just yet another kind of electromagnetic radiation fully described by Maxwell's theory. And then above that, we have gamma rays. And gamma rays span all the frequencies above that. They can be made lots of different ways. One of the most common ways on Earth is by nuclear processes. Now down below the infrared, there is all sorts of interesting radiations we use. There's the microwaves. And there the wavelengths go all the way up to about a meter. And these are what's used in microwave ovens. They're also what's used in some kinds of communication. And then down there we also have television, radio, Wi-Fi. All those kinds of waves are also electromagnetic waves. And below that you have the long wave radio.